Okay, week one, viscosity. Here we go. So last week we talked about, or this week, last video, I guess, we talked about just basic pressures and different uh, fluid properties like density and weights and specific gravities and all that good stuff. Okay, so now we're going to talk about viscosity. You will recall from the last slide set we were talking about there was a solid and water forming a puddle, and honey forming a puddle too, but at a much slower rate. Okay, so this is basically what we're talking about, viscosity. If any of you are car people, you might have talked about viscosity with engine oils and that kind of thing. So that's what we're going to talk about. Okay, what do we got here? Okay, so what are we going to talk about? We're going to define viscosity. We're going to talk about different types of viscosity, usually with fluids. Sometimes we talk about different types of viscosity, dynamic viscosity, kinematic viscosity, how to measure viscosity, and something Newtonian and non-Newtonian fluids, which might be a new concept for you. If you guys have the book, this is chapter 2 in the 7th edition of the Mott fluid book. Again, here it is. You guys probably have access to the PDF document of this as well. Okay. So, what is viscosity? Viscosity is the property of a fluid that offers resistance to the relative motion of the fluid molecules. So what's that mean? It's just how it resists to being put in motion. It can be thought of as sheer strength of the fluid. So, you know, ketchup has a higher viscosity than motor oil. But they're both liquids. Okay. Examples of high. So this is a viscosity graph. There's this unit called CP. We'll talk about it later on. It's a little bit dated, but it does show you how viscosity ranges in different fluids. We've got gases and liquids and something called paste. So acetone, we've got water, there's ionic liquid, don't ask me what that is, motor oil, and again, these can range quite wildly. Glycerin, maple syrup, honey, chocolate syrup, ketchup, fondue, don't mean to make you hungry. And then we've got something like toothpaste here. So examples of high viscosity fluids, fluids that have a high resistance to shear, honey, molasses, asphalt. I don't know if you guys have seen asphalt poured. It does sort of is liquid before it becomes a solid. Glycerin and crude oil. Examples of medium viscosity fluids: water, mercury, ethanol, alcohol. I got some of that in my medicine cabinet. And examples of low viscosity fluids: gasoline, gases. So things that flow quite easy, right? So where are we? Okay, energy loss. Energy is lost when a fluid flows, and this energy loss is largely due to the viscosity of the fluid. So the viscosity causes internal friction in the fluid. So you know about energy retention and energy losses. So here, what do we have? We've got a couple of different types of motor oil. I don't know if you guys have noticed this, but lots of times they've got these different classifications of motor oil. We've got SAE20 up to SAE50. Yes, the colors are different, but basically what do they have here? They've taken a steel ball, same steel ball, and dropped them all off in these test tubes, all at the same time, basically. We'll get into this a little bit later. And their rate of fall depends on the viscosity of the fluid. So the lower the viscosity, the ball's going to fall down faster. So the SAE20 probably has the lowest, and the heaviest, the SAE50. See, because they were all dropped off at the same time. Although you can't see that in a picture, but trust me, they were all, you know, just to see. In applications, the viscosity is important to certain functions of the system, as you can think of a car. So the exact viscosity of engine oil is an important function of the engine, right? So you need to have the right oil, the right lubrication within a car's engine in order to make it function properly. That's how they're designed. Okay. Viscosity. So the shear stress and velocity gradient, what do they have here? So this is, what are we showing here? This is, it's kind of a weird little diagram. You've got a stationary surface on the bottom, so say the bottom of a glass or whatever. We've got a fluid in it, and on the top is a moving surface. That's what's causing the shear stress, right? So it's the velocity, which is shown there, that V, okay? Got this fluid in the moment. Basically, generally, for the sake of this discussion, the velocity is a linear gradient here. So we've got on the stationary surface on the bottom, there's no motion of the fluid. It's not moving at all. And it's moving the most closest to where the moving surface is. On this point is the top, the moving surface there. So in this case, it's linear. So we've got the change in velocity, which is that Vy. Delta V is the change in velocity over the change in height. So basically the height relative to the station's surface. Okay. So in this example, it's linear. It's not always linear. We'll talk about this as we go along. So note at the boundaries, the velocity of the fluid is the same as the velocity of the boundary. So the stationary surface, the velocity is 0. Where the moving surface is applied, the top there, the velocity of the fluid at the top is the velocity of the moving surface. Okay. So continuing with the shear strength and velocity gradient, the velocity gradient is the change in velocity over the change in height relative to the non-moving surface, or the velocity over the height. This is only applicable if one of the surfaces is stationary, which is true generally. There might be a case in which you're having both surfaces move. Can't think of one right now, but it might come up. So these units are, so the velocity is meters per second. The distance from the stationary boundary is in length, so we've got length per time over length, so it just comes in per time. It's just a quirk of how these come up. So here, this figure that we've got, there's 2 plates with a thin layer of fluid between them, so it can be you can imagine, yeah, just like some sort of lubrication, oil. The lower plate is stationary and the upper plate is moving, so the velocity. So what do we got there? In this diagram, it's D, but it could be a delta, right? I mean, you guys are getting used to these different little nomenclatures, okay? So shear stress, we dealt with this before. Tau is the force required to slide one unit area of fluid over another, so in fluids, okay? So it's the applied force over the plate area is equal to the shear stress, this tau. So again, the units are force over area, so force over square lengths. In this case, for SI units, it's newtons per meter squared. Similar to all your other mechanics of materials courses that you've taken. Dynamic viscosity. So remember at the beginning when we talked about how there's different types of definitions of viscosity, dynamic and kinematic. So we're going to talk about the dynamic viscosity. The greater the shear stress, the faster the plate will move. So, I mean, usually. So the more shear stress, this tau that you're applying, the faster that the plates will move. Makes sense intuitively, right? So the shear stress is directly proportional to the change in velocity over the change in height, so this velocity gradient. So what did we do? We got this little factor that we're called nadir usually, so tau equals nadir divided by, or times the velocity gradient, change in velocity. So just rearranging it, same equation. Eta, oh, that's how they call it. So the constant eta is called the dynamic viscosity. It's sometimes referred to as the absolute viscosity or the coefficient of viscosity, depending on what book where you're learning, okay? For the sake of this course, we'll call it dynamic viscosity, okay? It's the constant for fluid given on its conditions, so temperature, pressure, all that good stuff, okay? But usually when it's reported at a certain temperature. When they do these tests, they figure it out at control conditions. So, okay, so what are these units of eta? As we discussed in the last slide, it's equal to tau, the shear stress, over the change in height, so the inverse of that gradient. So the change in height over the change in velocity. So what do we have here? Newtons per meter second. Remember, it's a pressure times what is the change in height is just in meters, and the velocity is meters per second. So one of the meters gets crossed off, canceled, and that per second comes up to the top. So we've got Newton times seconds per meter squared, or Pascal seconds, or if you're using imperial pounds seconds per foot squared. Yes, it's awkward, but such is life in engineering sometimes. So you'll find that different textbooks will use different nomenclatures, so they might not use this eta, they might use a different Greek symbol. So you might see mu for dynamic viscosity, you might see a U instead of a stylized V. So it's not just confined to fluid dynamics, it's in all engineering disciplines. We just have to be careful and consistent, okay? So yeah, for the purposes of this course, we're going to be using this eta. So alternative units, Pascal seconds is the standard unit for dynamic viscosity. It's used by all these different testing bodies. ASTM, you'll find that one lots. American Standards, Testing Materials, ISO, International Standards Organizations. I'm not exactly sure what the other ones are. Those are the two that I deal with the most. So you can refer to the book, section 2.2.1, for a discussion on other units that you may encounter. So poise and centipoise, remember that figure that we showed up before? There was that CP. So it's a obsolete unit for dynamic viscosity, and it's numerically equivalent to a meter pascal per second. Is it? 1 meter pascal is 10 point omega. 10, what we got here? Oh, 10 to the milli, so a millipascal. There we go. I've never used it, needless to say. But you'll see it. Sometimes you're given like old specifications for certain things, and you'll see it on there. And maybe books, old books. Sometimes you're sent to see these things. I mean, it's nothing, again, nothing you haven't encountered in your other engineering disciplines so far. Sort of strange units. So that's dynamic viscosity. Now we're talking about kinematic viscosity. And so another term is used to express viscosity. This is kinematic viscosity. It's sort of a stylized V, nu. It's basically the dynamic viscosity over the density of the fluid. So nu is equal to eta over rho. I know it gets a little bit complicated. It's easier when you're just looking at the Greek letters, eh? So there it is. So the units of this kinematic viscosity, nu, if it is, what are we calling it, eta over rho, so Pascal seconds divided by kilograms per meter cubed. So what's a Pascal? It's a Newton per meter squared. So we got Newton seconds per meter squared divided by kilograms per meter cubed. Rearranging it all, and you get these newtons per kilogram second meters. Cheese and rice. Keep going on, keep going on. A newton is a kilogram per meter, kilogram meter second squared. Force equals mass times acceleration. There it is. So you just keep going, and we eventually get to meters squared per second. Fun times, or square foot per second. So much like dynamic viscosity, there's these old units you'll probably hear your grandpa talk about, or in my case, my dad. So they got sent to Stokes, and it's probably, you might see it like in motor oils, that kind of thing. So what do they have? It's equivalent, numerically equivalent to a square meter per second. Okay, so 1 square meter per second equals 10 to the 6 millimeters square per second. That's why I sent to Stoke. And again, you'll see it published in books. So I guess the main thing, again, nomenclature and whatnot, is just to be careful not to mix up velocity, the V, with this new stylized V, okay? And that's why sometimes you'll see U used for velocity. I mean, you've probably seen it. I've seen it. You always kind of wonder. But you just got to keep it straight in your notes in your own head. So what's the difference between dynamic and kinematic viscosity? If you see the term viscosity without specifying dynamic or kinematic viscosity, just look at the units, right? So remember, dynamic viscosity is in Pascal seconds, and kinematic viscosity is meters squared per second. So just look at the units. In general, dynamic viscosity is more commonly used than kinematic, but because this is fluid mechanics, we're going to be using both of them, okay? But it'll be clear, it'll be written, just make sure you can read. Temperature effects on viscosity. So, as sort of alluded to before, viscosity is generally tied to temperature effects. So all fluids change their viscosity as temperature change. Some change a little, some change a lot. It just depends on which kind and how sometimes, you know, with engineered fluids, they're engineered to be a certain way, okay? In general, viscosity decreases as temperature increases. So we can take that same blob of honey that we were looking at before, and as you lower the temperature, as it gets colder, it's gonna not flow as much. It's going to be more resistant to shear stress. As it gets hotter, you know, you put your honey in your tea, it gets hot and it just flows like crazy, right? So high viscosity fluids tend to change their viscosity more when heated than lower viscosity fluids do. So what were the high viscosity fluids that we talked to? Honey, molasses, those kind of things. Lower viscosity, water. So, you know, as you change the temperature of the water, it's not going to be more viscous at 50 degrees C than it is at 10 degrees Celsius. More or less, okay? The relationship between viscosity and temperature is complex and cannot be expressed by a formula. Lots of times it's not linear, okay? The relationships are determined empirically, so through scientific analysis, and plotted on a graph called the viscosity index. So this is what it looks like. Viscosity index, in this case VI, it's a measure of how greatly the viscosity of a fluid changes with its temperature. So see this figure 2.5 and Appendix D of the book for plots of dynamic viscosity and temperature for various liquids and gases. Remember, fluids is going to be both liquids and gases. Okay, what do we got here? So let's just stare at this figure a little bit here. What do we have here? We've got kinematic viscosity. Oh, look at centistokes versus the temperature. So these are all different examples of different oils, apparently. So it tells me on this thing. They've all got different slopes, right? The slope of that line is always a little bit different. So their viscosity index is different. We've got ranging from 250 to 0, right? But at some point, at 40 degrees C, for some reason, they all have one point common, this 100 centistokes. So all the oils have the same viscosity gradient, I guess, but different indexes, okay? So how does the velocity affect viscosity? So the equation for the dynamic viscosity, you'll remember tau equals eta times the velocity gradient. And it's only valid for Newtonian, i.e. ideal fluids. These fluids exhibit a linear relationship between the shear stress and the velocity gradient. So remember, I sort of teased you with this Newtonian and non-Newtonian fluids. This is what we're getting at. For other fluids, eta, the stylized n, is affected by the velocity gradient. So the relationship between shear stress and the velocity gradient, it's not consistent. These fluids are called non-Newtonian. So basically we got Newtonian, where everything's a nice little line, and we've got these non-Newtonians where it's not a nice little line. We've got a graph here. What do we got here? We've got velocity, if we look at this A figure, shear stress tau on the y-axis, and velocity gradient, change in velocity over change in height on the x graph. And for a Newtonian fluid, remember, it's just a nice happy little line. It's a linear relationship between the shear stress and the velocity gradient. There's also these, let's see now, what do we have here? We'll start at the top, that Bingham fluid. You can see it's still a line, but it's a lot steeper of a gradient. It takes a lot for that shear stress to get it going, to get to the same velocity gradient. We also have a, let's see now, what's our next one? Pseudoplastic. We'll get into this, don't worry. Just looking at the figures now. We've got sort of a the shear stress and velocity gradient is a little bit different shape than the Newtonian. You can see it's above the Newtonian fluid, this linear relationship. And then we've got, is it a dilettante? Whoa. Fluid, which is below the Newtonian gradient. So that's shear stress. If we look at the other graph B, we've got the apparent dynamic viscosity, that same thing. So this is that constant, right? So what do we have? It's not a constant in these cases, right? So Newtonian fluid, it's a constant. So that, again, it's that same sort of concept. It's just a line. And what else do we have here on this velocity gradient? If we look at the Bingham fluid, that one is, okay, well, look at it. Oh, it's a steady gradient too. So it's similar. If we look at that shear stress, it's just lower than the Newtonian fluid. And if we look at the pseudoplastic, we've got it's got like a negative slope and sort of increasing as it goes along. And the dilettante is increasing in an increasing manner. Again, we'll get into it a little bit more, I'm sure, right? So Newtonian fluid, the shape eta, that stylized N, for dynamic viscosity, it's constant for a Newtonian fluid. Therefore, this linear relationship is valid. So we got tau equals eta times the velocity gradient. So examples of a Newtonian fluid: water, gasoline, oil, alcohol, glycerin. These things all behave in a linear fashion with shear stress. Okay. Non-Newtonian fluids, dilettante. So this, here we go. We've got shear stress and the velocity gradient. So the slope is not constant. It's low apparent viscosity. Slope is start, and it increases as the velocity gradient increases. So as the change in velocity over the change in height, as it increases, so does the slope of eta. Okay, you can see it there in the figure. The plot of shear stress versus velocity gradient lies below the straight constant slope for the Newtonian fluid. So you'll remember that from this guy here. Okay, so it's below. Examples are slurries with a high concentration of solids, such as starch solutions, titanium dioxide, which is apparently a paint ingredient. Okay, so I guess we'll get into it. What is a starch solution? We'll find out. Okay, we'll be working with all this stuff. So pseudoplastic fluid. So this one here, we've got, it's shown graphical representation, shear stress over velocity gradient. The slope isn't constant. It's high apparent viscosity at the start and drops as the velocity gradient increases. Okay. So if you plot the shear stress versus the velocity gradient, and it lies above the straight constant slope for the non-Newtonian, or for the Newtonian fluids. Oh, what example? Blood, ew. Molten polyethylene, latexes, syrups, adhesives, molasses, inks. Bingham fluids, okay. So the minimum shear stress is required for the fluid to move at all. So like you can put that plate on it, stress it out, nothing happens, and then all of a sudden it moves, okay? Once the flow starts, there's essentially linear slope in the curve indicating a constant, so it does have a constant eta too. It just takes a lot of shear stress, pressure, to get it to start going. So examples of this: chocolate sauce, ketchup, mustard, toothpaste, paint, wet concrete. I don't know if you guys know this, but concrete is initially a fluid. When it comes out, it turns into a solid. Sewage sludge. Ugh. I don't know if you guys have taken sewage course yet. It is very interesting. So these are also known as a plug flow fluid. Okay. Time-dependent fluids. So these are fluids that exhibit apparent viscosities that vary with time as well as temperature and velocity gradient. Cheese and rice. Things are getting complicated, eh? So examples of some crude oils at low temperatures, printers, inks, nylon, polymer solutions example. Okay. So note that liquid polymers are utilized in water and wastewater treatment processes that are of interest to civil engineering technologists and engineers. Okay. Polymer is a very large organic molecule that has a positive and or negative charge. They are used as flocculants that clarify and thicken and dewater applications. I don't know if you guys, maybe we'll talk about it on Wednesday, whether you guys have had any, if you guys know what a flocculant is. Basically you mix it in and it causes, the polymer causes suspended solids within the liquid to coagulate and become large they call it curds in here, so larger blobs of material, so that eventually the flock will get so big that it'll just eventually start falling out of the fluid. Okay. And yeah, so why do we care about this? If you're trying to get any impurities out of drinking water, if you're trying to clarify sewage treatment, I'm sure you have seen those movies where people drink their urine because they can purify all the impurities out of the water, out of the urine, in order to make it drinkable again. I know, a little gross, but guess what? I think it's the wave of the future. So here we go. I'm going to do my best to try to pronounce this. Electro-rhetorical fluids and magno-rhetorical fluids. So ER and MR fluids. So these are actively adjustable fluids. I mean, I'm sure you can get it by their names. So they behave as other fluids normally do, but they're a little bit different in their properties. So this includes the viscosity, which we're talking about now. In the presence of, in the first ER, so electrical currents, and in MR, magnetical fields. Okay. They are suspensions of particles in the base fluid. So again, it's like a fluid with little bits of things in it. Okay. So in the case of the ER fluid, when electrical currents are applied, they turn into gel and behave more like a solid. And with MR, when a magnetic field is applied, they become virtually solid. So you can read a little bit more about this in the book, section 2.4.2. Okay. Nanofluids. This kind of reminds me of Star Trek all of a sudden. So fluids that contain extremely small, so less than 100 nanometers, 10 to the negative 9 meters. So extremely small particles within the base fluid. So it can be water, what is it? Ethylene glycol, oil, biological fluids, etc. Okay. Nanoparticles can be metals such as aluminum and copper, silicon carbide, copper oxide, graphite. I mean, I'm sure you can imagine sort of little bits of particles in fluids. It happens all the time. Nanoparticles have a far higher surface to volume ratio than the base fluid. The mixture in the fluids, the mixtures, the suspensions, and it sometimes enhances the thermal conductivity of the fluid itself. So this is used for cooling electronic devices, lubrication, biomedical, drug delivery, all that kind of stuff. I mean, I'm sure you can think of, is it in here? No. Like any kind of cooling process that needs to happen in industrial plants. So how do we go about measuring viscosity? So here's one way. These are usually set out by different testing bodies. They tell you how to do this. So one of them is the Sabelt Universal Viscometer, and it's basically a time to fill a 60 milliliter volume, and then it's recorded and you convert that using pre-calibrated tables. So basically it's a machine. You got a reservoir of fluid held at a constant temperature. Remember how we said viscosity is dependent on temperature, so they got to keep it at the same temperature. There's a little outlet, and they take time. They measure the time to fill up the flask. Look at it against tables and figure it out. So this one, remember when we talked about this before? Way up. Let's go up. This guy here, okay? If you recall, boop, all the way back down again. It's the same sort of thing. So we've got a falling ball viscometer. Very innovative name. The ball is assumed to be falling at a constant velocity, i.e. terminal velocity. So you've got a sample fluid, you got a ball, you dump the ball into the fluid, you measure the distance, time it takes, guess what, there's the velocity. Whee! So how do you go about finding eta? Remember that little stylized N? We've got which is the dynamic viscosity. It's equal to the specific weight of the sphere, remember the ball that's in it, minus the specific weight of the fluid. So this is in newtons per meter cubed, or weight over length cubed. You got the diameter of the sphere, so that's a meter squared, and the velocity of this sphere, meters per second, okay? Nice little easy little equation. Gamma S minus gamma F. Multiply that by the diameter of the sphere and divide it by 18 times the velocity. Okay, Stokes' law. This is where it comes from. Okay, so the theory behind the falling ball method is determined viscosity is derived from something called Stokes' law. So if you're interested, see the book. Section 2.6.4 and 17.5. So spheres falling freely and slowly through a fluid reach a terminal velocity. So, you know, it might start off small and then gain some speed because of gravity and eventually hit terminal velocity. So here the downward force, the weight of the ball, is balanced by the upward forces of buoyancy, which we'll get into it later on, and viscous drag acting on the sphere. We'll talk about all this later on, so don't worry. I mean, you might instinctively know what buoyancy is and maybe drag. So drag is comprised of the pressure drag and the friction drag. So there's two different types of drag. And we'll get into this again. It's just sort of why the fluid is trying to stop the sphere from moving. So Stokes' law. In very viscous fluids, when the Reynolds number, so get used to this too, we're going to go into Reynolds number, but for now, Reynolds number, it's denoted as capital N with a subscript R, capital R. It's very low, ideally less than 1. The drag is almost 100% friction drag. So the equation given above for the dynamic viscosity applies. This guy here. Boop. Where are we at? That guy? Yeah. Okay. In this condition, no turbulent wake is developed behind the sphere. So flow streams around the sphere do not separate. So what's this mean? Basically, the fluid's not moving very fast. Okay. If the Reynolds number, so that NR, increases to approximately 10, weak eddies. So eddies are those little whirlpools that develop behind. If you look at, say, if you're looking at a river and you see a rock and you can see the river flowing past the rock and then all these little whirlpools come in, that's what an eddy is. So as the Reynolds number increases to approximately 10, weak eddies, so these tiny little eddies, begin to form behind the sphere, and this is pressure drag as well as friction drag is forming. When the Reynolds number is approximately 1,000, the wake is fully developed and pressure drag accounts for approximately 95% of the total drag of the sphere. So what do you care about this? Reynolds low less than 1. It's 100% friction drag. When it's greater than 1,000, 90% of the drag will be pressure drag. Okay. Stokes' law, here we go. Reynolds number will be discussed in detail for sure. You'll eat, sleep, and drink Reynolds numbers soon. But it's basically a dimensionless number that's used to measure how turbulent a flow is. For the study of drag in bodies for a fluid, Reynolds number is given by, so we got this Reynolds number, NR, times rho V. Are we saying V is the oh yes, it is. It is the so the speed of the fluid times the diameter of the body that's in it divided by eta. So it ends up being what do we have? 2 different V's. So we got the flow rate, speed times the diameter divided by these V's. Again, we got to keep this stuff straight in our heads, which we will. Stokes' law is an important concept for civil engineering related to the applications that rely on settling of soils and still water. Okay. A lot of this course is geared to water treatment and sewage treatment. There are other properties of fluids too. I think the number 1 use of computer power is actually for fluid dynamics. But most of the time we consider something being, like I consider something being fully turbulent, so it's but if you're trying to remember how we talked about flocculation, if you're trying to get these large particles to settle out of fluids, then you want this Reynolds number to be slow so it doesn't keep things suspended. Okay, I mean, you stir the coffee and you suspend the particles, right? For example, in sewage treatment, primary and secondary clarifiers, essentially settling ponds. Again, I'm not sure if you guys have gone into this, so about different types of sewage treatment, but there's primary, secondary, tertiary, different types of clarification. So primary and secondary clarifiers, settling ponds, septic tanks. I don't know if you guys have had much experience with septic tanks, but my parents have a septic tank. Sewage lagoons, I know, it's almost as gross as it sounds, etc. Similar processes are used in water treatment, stormwater treatment, oil grit separators. You'll see this lots in parking lots. Okay. So here we go, problems. Again, we'll do these on Wednesday, but I encourage you to try them out first. So I'll just read them out. So problem 1, again, this is that falling ball thing. So you got a 30 millimeter diameter ball. It falls 43.6 meters in 1.5 seconds. Wowzers. The temperature of the fluid is 20 degrees C. The specific gravity of the ball is 1.9. And the specific gravity of the fluid is 0.94. So try to figure out what the fluid is. Again, you're gonna go through the back of the book, or there might be, I don't know if we published it, just look in the back of the book, okay? Or look it up on the internet. Just make sure you've got a couple of different sources so you're not relying on one internet source that could be goofy and wrong. So problem 2. Dynamic viscosity, eta, and kinematic viscosity. Oh, there we go. So what do we have? We got a stationary plane. We've got an area of a plate that is 3 square meters. We've got a force applied at 270 newtons at a velocity of 0.5 meters per second. The fluid is oil, so its rho density is 90 kilograms per meter cube. So just try to find out the dynamic and the kinematic viscosity. Easy peasy, fresh and breezy. Oh, just 2. Yay, you guys got off. So, like I said, we will do both from the first video, the basic concepts of the fluids and pressure, and we'll do this viscosity stuff. We'll do all of that on Wednesday, okay, at 10:30. I'll send you, like I said, I'll send you a Zoom link. You guys can log on in. I'll be recording them both too, so I'll put them up, okay? Happy first week.